Okay. Hello, everybody. Welcome to today is Wednesday, the 24th. Couple of announcements. There's a homework. The penultimate homework is due today at 5. The last hour exam is tomorrow morning at 9:15. I sent an announcement out about the details on that exam. The main thing to emphasize is that to be sure you're there on time. We had 1 or 2 students show up late last time. That can't happen anymore. Today we're going to look at the last main concept for rotations, which is the concept of angular momentum. But before we do that, we have to mop up a couple of things. The first is we want to look at conservation of energy with rotations, and we want to review the vector nature of rotational quantities, or at least sort of set that up. This is a result from a problem that I did yesterday, in the sense of, we did a solid sphere, radius r and mass m, on a ramp of angle theta. We worked out yesterday that there's a force of friction on the ramp. If there's no slipping and no sliding, it's the friction that causes the sphere to rotate. And we worked out that the acceleration down the ramp was 5/7 g sine theta, using the recipe of applying Newton's law, second law of rotation, with also the second law of rotations, the whole recipe for dealing with extended free bodies and so forth. But I want to ask a different question today, which we set up yesterday, which is if I release the ball so that the bottom of the ball is at some height, which I will define as a given parameter h, and I ask what is the velocity of the ball when it comes off the ramp, when it reaches the bottom. This is a problem that could be solved in principle with constant acceleration once you have it, but an alternate scheme and a faster scheme is conservation of conservation of mechanical energy. And remember, the condition for conservation of mechanical energy is that the forces are either conservative, weight, or do no work, normal. But the force of friction here is not conservative, but we're going to get away with this anyway, because even though the force of friction here is being applied in the opposite direction of the motion, it's being applied so that it has one effect, which is to put a rotational energy into the spinning object. There's no slipping or sliding here, so there's no work done at the point of contact. It's all going into the rotation. So we're going to basically keep a notion of rotational energy. Let me write this out in longhand so I can have that. Ooh, that needs work. So I've got the total kinetic energy, I wrote this last time, is equal to the translational kinetic energy plus the rotational, well, I'll just call that K rot, which is equal to 1/2 mv squared plus 1/2 I omega squared. That's true in general. So we keep this in mind, and then we say, okay, let's apply conservation of mechanical energy to this problem, where this is the before and this is the after. So in the before case, so we just, first of all, let's just write it all out. So we say u plus k is equal to u prime plus k prime. So it's always good to start with that step. So u is going to be mgy. K is going to be this total now, 1/2 mv squared, and we'll put in this particular values for these once we've written it out, plus 1/2 I omega squared, and that's equal to mgy prime plus 1/2 mv prime squared plus 1/2 I omega prime squared. Sorry, that's a little crowded there. Omega prime squared. Okay, so now once we've written that whole thing out, then we can consider what we know about the setup. So in the before setup, y is equal to h, because that's where we're starting from. That corresponds to the position of the bottom of the ball. And the initial velocity, if I release that rest, is 0. So on this side, I've got mgh plus, well, 0 plus, well, this is not rotating either, 0. And that's going to be equal to, at the bottom, y prime is equal to 0. And we've got some particular values for v prime and vf. Well, vf is just v prime is just vf. This will be 1/2 times, oh, this should be big M, because I said that's up to the mess, sorry. So big, 1/2 big M times, mgy is 0. So this is equal to 1/2 m the final squared plus 1/2 I, which we have, times omega prime squared. So we have to basically contend with this omega prime. So how do we do that? So let me, I'm going to finish the work here. So I'm going to erase here and then basically finish this equation here. I'll erase this equation here. So we'll jump back to this location here. So we've got on this side mgh is equal to, because that's 0, 1/2 big M, so these should be big M's, m vf squared, which is what we want. That's great. Plus 1/2 times I, let's plug that in, which is 2/5 m I squared. And then the question is, how do we deal with omega prime? And the answer is we use the same thing we keep using before when we're dealing with going back and forth between rotational and linear quantities. And that is that we use the rolling constraint. So let me write that over here. So the rolling constraint says that V is equal to omega times R. So in this case, if I want omega, I can just basically use the rolling constraint, which basically tells me that omega is equal to V over R, because that's what we've got here. I just solved for omega, but that's now the final velocity, Vf over R, that quantity squared. Okay. So basically, I just took the value of omega, which I didn't know, and I used the rolling constraint to plug it in. The rolling constraint for velocity, not for acceleration. We also have A equals alpha R. That's what we use when we do acceleration, but we got velocity here. Okay. And then the rest is just algebra, and it's kind of not that interesting, but let's just see what we get. So we get big M times GH equals, well, let's see what I've got here. I've got, well, look, that's squared. So those R's cancel. That's nice. And I've got 1/2 times 2/5, that cancels. So I end up with 1/2 mv f quantity squared plus 1/5 mv f quantity squared. Oh, okay. So that's looking kind of interesting. So I solve for VF. So I basically, oh, the M's all cancel. So let's get rid of those. That should be big M, right? So on this side, so just to, again, give myself a little bit of room to finish up the algebra, I'll erase this now. So I basically move everything over here. So I have 1/2 plus 1/5. I have 1/2 of a VF plus 1/5 of a VF. So 1/2 plus 1/5 is 5/10 plus 2/10. That's 7/10. So I've got 7/10. That's kind of a weird number. VF squared equals GH, or V sub F equals the square root of 10/7 GH. That's kind of a funny answer. The units look good. This is meters per, this is length over time squared times the length square rooted gives me a length over time, so that makes sense. Notice that this answer is similar to, but different from the answer if I had simply no friction. I had no friction and just something shooting down the ramp. The final velocity was equal to 2 CH. So now the final velocity is less than 2. It's more than, it's 10/7. That's a number. That's less than 2. And the explanation for it, of course, is that while I'm rolling here, I have two kinds of kinetic energy, one in the translational form and the other in the rotational form. And those two together are the original energy. So that means if I'm going to be rolling when I get to the bottom of the ramp, I can't be moving as fast forward because some of that energy that I had to be moving has to go into the rotation. Okay. Any questions about that? So one nice thing about this, of course, is that it gets you the answer without going through any kinematic technicalities or trigonometry at all, really, once you've got H. The other nice thing about it is that this would be true even if the shape of this ramp was not smooth. If I had some kind of wobble like this, the ball went up and down. The details of the path don't matter for conservation. All that matters is the initial position and the final position. So you can solve problems like that.
Professor, can you explain again why we can apply energy given that friction's non-conservative?
So, okay. So the answer to the question is twofold. One, I've pulled a swindle on you. I'm waving my hand. Okay. The swindle, the details of the swindle come in the context of two different issues. One issue is that even though the force of friction is applied on the ball, at the point of contact, that force of friction is not moving the surface of the ball. In other words, the ball is at that instantaneous, as the ball rolls, so here's the ball rolling down, right? At the point of instantaneous contact, even if there's a friction force there that has contributed to the overall motion of the ball, at the point of contact, there's no motion. There's no displacement of that force over on that object.
Oh, okay, yeah.
So that's now, having said that, that's somewhat of a swindle, but
Okay.
but nonetheless, it's good enough for what we're doing here. A deeper answer is that you have, how can I put it, that this set of rules we have of conservation of energy is a good set of rules if you're thinking about problems that are not too general. The right way to generally deal with this is to deal with a completely different kind of formalism for mechanics, which is not part of this class, but nonetheless, it's true. The other reason we get away with it is because in this case we enshrine the energy that the force of friction actually isn't doing zero work. It's doing no work at the point of contact, but in fact, it contributes to the rotation of the object. And so that even though there's a force doing work, that work is actually encapsulated in the our expanded definition of energy. So in other words, this term here corresponding to the rotational energy is now included. So as long as we include this term, we can contend with it.
Okay, thank you.
But you're right, I've sort of cheated. I haven't properly shown you why this is true. And to do that is basically means I have to step away and show you why the framework we're using here is accurate and true, but not as general as you might think it is. Any other questions? All right, let's do one more example with conservation of energy. And again, it's an example that we're familiar with. It's the rod on a hinge. So let's go back to the rod on the hinge. So I have some arrangement like this with I've got a hinge. And let me color the hinge slightly different so we can see it distinct. So I got the rod. So the rod, so when I say a thin rod, I mean a rod whose length and is much larger than any other dimension of the object, so that you don't have to worry about it treating it other than just basically a long stick with some hinge point there. And so the rod will have length m. The rod will have mass m and length. We'll use little l for today because we're going to use big L for something else. I'm going to do the same thing I did before. I'm going to release it at rest. And remember, last time what we did is we worked out the acceleration of the center of mass. But this time I want to ask a different question. I want to ask the question, suppose we let the rod fall down, so it swing down so that it basically goes, ooh, and it comes whapping into, it basically comes slapping into the wall, right? So, you let it go like this, and it comes slapping down, whap. And I want to ask the question just before it hits, as it's rotating in there, what is the final angular velocity of the rod? Okay. So we said we noticed from last time that the free body diagram was pretty straightforward. It included a weight force here. It also includes a hinge force. We argued and demonstrated that the hinge force when the bar is at the top was zero, or sorry, the horizontal force was zero, and so the hinge force was only vertical. But that can't be true as the object swings through. As the object is swinging through, for example, as it's, if it's off at this angle, say, at this particular time, the hinge force must be both lifting it up and keeping it against the wall. So at any arbitrary time, the hinge force could be pointed in any arbitrary position. And it might be pointing along the bar, but it might not be. We don't know. We just have no idea what this hinge force is doing. Whatever it's doing is a function of time. It's quite complicated. So, so again, we're not going to use Newton's laws to solve this problem, but we can ask the question, what about conservation of mechanical energy? And so what's our approach? Our approach is, well, what are the forces? So the conditions, the weight force is conservative, the hinge force in general is not conservative, but I'm going to make the same hand-waving argument I made before, and that is that even though the hinge force is not conservative, at this particular point, it's not being applied over distance. It's being applied just at that fixed point. Right? You see what I'm saying? Okay. So I'm going to, in the special case, I'm going to basically say, no force over distance is the way to, over distance, right? So that lets me use conservation of mechanical energy. Again, as long as I've got the concept that the total kinetic energy is equal to the sum of the two types, translational and rotational. So I could charge off and solve the problem, but there's one more thing I want to think about, and that is for any conservation law problem, especially conservation of energy, you have to pick a reference point. In other words, you have to define the location that you're going to set equal to the zero position. Or you got to define, in some sense, the word where you're going to measure the concept of both kinetic and potential energy. So for potential energy, we don't have a choice, right? We have U equals mgy, but the question of which y we use is not optional. We have to pick a y corresponding to the center of mass point. So, this basically is YCM. I can pick any point for my coordinate system, but I can't pick any point to the position of the rod. I have to choose the center of mass. As far as gravity is concerned, this thing is an object that is concentrated at its center of mass point, and that's all it is to it. So when I work out potential energy due to gravity, this is the expression I have. What about kinetic energy? Well, in principle, the kinetic energy is equal to the sum of the translational kinetic energy plus the sum of the rotational kinetic energy. And one option you have, it's an option, is that you can treat it just like we treated the sphere rolling down the ramp, which is to say we consider the translational motion of the center of mass, and then we add to it the rotational motion as the ball rolls down the hill. And you could do that here. You could calculate basically the component that corresponds to the velocity of the center mass as it goes down, and you could add to it the component of energy corresponding to the rod turning about that center of mass. But the problem is that the rod is not turning, well, it is kind of turning about that center of mass. It's anytime the rod's turning, you can say it's turning at some point. You get a choice of points. But that's not the natural place to define the rotation of the rod in a problem like this. The natural place to define the rotation of the rod is at this hinge, at the pivot point. And from the point of view of the motion of the rod from the pivot point, if I say this corresponds to the reference of the point of rotation, then this motion, from the point of view of this location, this bar is not translating at all. It's just rotating. And the amazing thing is that if we apply conservation of energy, we're allowed to choose any point we want as the position at which we will calculate translational and rotational motion. We could calculate it here, in which case we'd have to deal with both translation and rotation separately, or we could just pick the hinge point, in which case the road motion is purely rotational. Okay, so it's a subtle thing. Why now? So in other words, we're going to argue that in this case, the total kinetic energy is equal to the translational kinetic energy, which we set to 0, plus so in other words, purely rotational, which is the 1/2 times I times omega squared. The only thing that we have to be careful of is when we say I, what do we mean by I? We mean the moment of inertia, the rotational inertia of the rod as measured at that pivot point, right? Because remember, a rod, if I have a rod and I measure its rotational inertia at the center of mass, this is what I showed in the video last night, that this thing is 1/12 m times L squared. But the rotational inertia of a rod at the end, rotating about one end, is 1/3 m L squared. Which of these, you get a different answer depending on whether you choose this is the point of rotation or this is the point of rotation. So what we're going to do is we're going to choose the end of the rod as rotation, which means this is the equation we want to put in here. Okay, so there's this conceptual setup for this problem that in order to contend with the kinetic energy, we choose the pivot point at one end. Since that pivot point doesn't move, it has 0 translational kinetic energy, and we use the moment of inertia calculated for rotation about that pivot point. Cool. So now we can actually go ahead and apply conservation of energy to solve the problem, and it becomes quite simple once you set it up this way. So let's do it. So we say U plus K is equal to U prime plus K prime. That's conservation of mechanical energy. I'm going to put that in there. So we write down, let's just write that longhand U, mgy plus, so we're already going to say that K translational, we're going to set that equal to 0. We're not worried about the velocity so it's just going to be 1/2 I omega squared. That's equal to mgy prime plus 1/2 I omega prime squared. Okay, so now we just plug in the before is up here, and the after is right when we hit. So so we have to contend with the position. So again, y is the position of the center of mass. So let me emphasize that, cm. Even though I'm doing the kinetic energy about the hinge, I have no choice. I have to do the potential energy about the center of mass. So I'm going to pick a reference position, and I always like to pick the reference position, y equals 0 at the point of rotation. So that means I'm going to basically set the initial position to 0. So in other words, this will become mg times 0, because that's what y is equal to 0. And then, so y equals 0. And then when it swings down here, y prime, that's just equal to the length over 2, but it's negative because that's fallen down, okay? So 1/2 mg0 plus the initial speed, well, if I release at rest, it's 0. That's equal to mg times L over 2 minus, there's a minus sign in there, plus 1/2 I omega final squared. So everything's all done except I have to plug in i's and solve for omega f. So so happily this side is just 0, and that negative side basically, you know, I got a 2 here and a 2 here, so I get I omega f squared equals mgl. So that's nice, right? Because I just multiplied both sides by 2 to get rid of the 1/2 there. So we bring the omega f squared is equal to mgl divided by I, which we said is 1/3 ml squared. So we get that this is equal to the m's cancel. One of the l's goes away. So we get that this is equal to E times G times, that's 3G over L, sorry. I've got everything there, and of course I have to take a square root, okay, to get omega final. Just make sure I've done my algebra right. So we get the 1 over 1, the over time square, length over time squared divided by a length is 1 over time squared. Yeah, it looks pretty good. Okay, any questions about that? The key to setting up this problem so that the algebra is tractable is to choose the pivot point as your reference position for the kinetic energy, because in that case, the kinetic energy is purely rotational. You don't have to deal with the translational term. It gets set to 0, because from the point of view of this position, the rod never moves. It's never translating, never shifts in X and Y and Z position. Okay, questions about that? All right, I want to go on to a couple of one last mop-up concept, and that is the concept of the vector notion of rotations. So sometimes when I teach this course, I start with the vector notion of rotations, but I found that the vast majority of problems that you hand off on the homework don't require it. So this year I've said, okay, let's do the vector nature of rotations later, which I think is actually a good idea, because you don't need them to solve problems, just the same way you don't need the vector nature of forces to deal with Newton's second law. But nonetheless, quantities of rotation do have a vector nature. So I'm going to consider here, I've got, step back just a little bit, it's a bit of glare there. This is an old DVD disc, and I put it on my finger, and it has the usual, sort of put a little mark on it on this side to indicate the sort of 0 position. I'll hold it like this. And then if I spin it, here it is spinning in what I'm going to define as the positive, which is say the counterclockwise direction. I can talk about that motion. I can talk about the angle theta relative to the horizontal. I can talk about omega, the rate of change of position, and if I make it go faster, I can talk about acceleration and torque. It all makes good sense. But suppose instead of doing it like this, I did it like this. So now it's pointing off to the side. It's the same story, but it's not pointing the same way. If I want to talk about the vector that corresponds, for example, to the rotation of the wheel, there goes the wheel around. Let me put it on something that'll spin even faster. There goes spinning. Woo. All right, there you go, like that. How do I represent that corresponds to angular velocity? I mean, if I have a particle moving, the vector velocity corresponds to the displacement of the particle at a time. In other words, the path, the velocity vector corresponds to a tangent to the path of the particle as it goes through time. If the particle is moving at any given time, the velocity vector corresponds to a headlight that's basically pointing in the direction of motion. But that's not quite true for omega. Omega, basically, the problem with rotation is it comes back on itself. It doesn't go anywhere, and yet it still has a vector nature. So how do we define that vector? So you might be tempted to define the vector based on the motion of the wheel itself. So if I pick, for example, if I pick this location of the 0 point, if it's moving this way, there's a little bit of velocity vector up. You could say, well, maybe that velocity vector and omega are somehow connected. Maybe they point the same way. But the problem is that when same wheel on the other side is going down. And likewise, the top and bottom, they go opposite directions. So all the directions that are in the plane of rotation correspond to motion of the wheel, and they all cancel each other out, at least as far as some way of dealing with it. So we don't want to be in the plane, so that suggests that we want to be out of the plane. So in other words, our idea for the vector corresponding to motion is a vector that points along the axis. It's the axis of rotation that defines the motion. So if I'm basically spinning this way, then the axis, it's the axis of rotation this way. It could be this way, but of course I can spin the wheel the other way. Does that change it? And if it does change it, which one's which? How do we deal with it? So our approach then is we have a spinning object. So here I'm going to take like a disk, and I'm going to kind of draw it in perspective here. And that disk is spinning about an axis. So there's an axis that comes in, and then dot, 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 and then comes out on the other side, something like this. And I want to basically define a direction. And so the way we define the direction is we use something that physicists invented a long time ago. Turns out the answer to the question of which way is positive and which way is negative is the same as like the charge on an electron or proton. As long as we all agree, it doesn't matter. So what are we all going to agree on? So we're going to agree on something called the curly-fingered, curly-fingered is my name, right-hand rule. Okay, so here's the good news. In physics, it has nothing to do with biology. In physics, we've all agreed that whenever we get into this situation, we use our right hand to solve the problem. Okay, in physics, there are several right-hand rules. You see the right-hand rule repeated over and over in physics. There is never a left-hand rule. So if you're working on a problem and you're right-handed and you need to figure out the right-hand rule, put your pencil down, because if you pick up your left hand and do it, you'll get it backwards. Always use the right hand. How does the curly-fingered right-hand rule work? It's simple. The curly-fingered right-hand rule says that what you do is you wrap your fingers around in the direction of the rotation. So if this disk is spinning as seen from above in the counterclockwise direction, I'd wrap my fingers around like this. See what I'm doing? If I do that, your thumb is pointing along the direction of omega. That's omega. Now remember, we already defined the line that's perpendicular to the rotation as the orientation of the velocity vector. What the curly-fingered right-hand rule does is it breaks the ambiguity between going this way versus going that way, right? If the disk were spinning in the opposite direction, I'd use my curly fingers this way, and it would point downward, right? So this gives you an orientation of omega, right? And the same curly-fingered right-hand rule works just as well for alpha, at least in the case when omega, when the velocity vector is simply corresponds to speeding up. If I start speeding up, in other words, if d omega dt is basically increasing this way, then the vector alpha is pointed along that, again, according to the right-hand, curly-fingered right-hand rule. Curly-fingered right-hand rule. Okay? Make sense? The curly-fingered right-hand rule also works for torques if you've figured out the direction of the twist. if I have a torque, right, if I'm basically going to, you know, twist the bottle cap, I've got to twist it, and just, by the way, bottle caps in the United States are all right-handed, right? Which is to say you grab them and you want them to come up, you twist to this way. Again, curly-fingered. That corresponds to the direction of the torque. Okay? So that's the curly-fingered right-hand rule. It tells you the direction of rotational quantities once you know how the object is spinning. You curl your fingers in the direction of the rotational quantity, and your thumb gives you the orientation of the vector. So again, this is a vector that points in this direction. This is a vector that points in this direction. Okay? So far, so good? So now I got to add one more thing, and that thing is the vector cross product, which we've dodged around all semester, but now we're going to deal with it. So we have curly finger. That's a conceptual definition. There's a slightly different hand rule for the cross product, so we want to deal with that. It's sort of the same, but it's sort of different. Okay, so I have to go back to math. Vector cross product. So you remember, we had the dot product, which said that the scalar product of two vector was the magnitudes times the cosine of the angle, and that was the scalar. But now I'm going to define a vector cross product, C, which is defined as A cross B. Okay, so I've got two vectors, A and B, and I want to find the cross product C. So what's the rule? Well, the first rule is that the magnitude of C, sorry, that's supposed to be magnitude of C, is equal to A, the magnitude of A, times the magnitude of B, times the sine of the angle phi between them. All right, so that looks familiar. That's just like the torque, for example. All right, so that's great. But which way does it point? The vector C points, well, it does two things. Is so that C is perpendicular to A, and C is perpendicular to B, and C is obeys what I'm going to call the other right-hand rule, by the right-hand rule. So the perpendicularity basically says, okay, I got to be off the plane that A and B make. So for example, in this case, I wrote A and B both on the chalkboard. That means that the vector C, which I'm going to represent by this arrow, this ruler, has to point perpendicular to the chalkboard. In other words, it's coming towards your nose. Okay? A cross B must be a vector that's pointing perpendicular to this. And this is the fundamental definition. If you ask the question, which way does it point? That's the answer. It points perpendicular to both A and B. And the only ambiguity is, does it point with the arrow coming at you? Or does it point with the arrow going away from you? That's the only question. And to resolve that ambiguity, we use something called the right-hand rule. Now, how can I put it? If you have a bunch of physicists in a bar late at night and they're tired and grouchy, and you want to start a fight, ask them to tell you what the favorite way of doing the right-hand rule is. And you'll get, everybody will tell you a slightly different way. You can use any method you want as long as it works reliably for you, as long as it gets you the right answer. I will give you my two favorite methods for doing the right-hand rule for a cross product, okay? So the first method is what I call the limp-wristed right-hand rule. Limp-wristed because I don't keep my wrist, like I let my wrist flap, okay? And the rule works like this. Point your arm in the general direction of the first vector, A. Swing your hand, your wrist from A to B. Then your thumb will point in the direction of C. So in other words, again, it's got to be either into the board or out of the board. So I point my arm in the general direction of A. Here I am pointing my arm. Then I swing my wrist from A to B, like this. Okay? I have to rotate, if I need to, I got to rotate my wrist until I can go from A to B. Thumb points in the direction of cross product. So in this case, the cross product is out of the board. Often out of the board is represented by a little target with a dot into it. Imagine an arrow piercing a piece of paper just about to come out to your head. Okay. What if I do it this way? Suppose I do here, I'll do A pointing up and B pointing in this direction. What's the cross product then? Which way does it point? Again, I've drawn them both in the plane, so it's either into the board or out of the board. One of those two choices. Do this first. Don't go to the right-hand rule until you figure out it's either this or that. Because if you have it pointing any place other than perpendicular to those vectors, it won't work. So, but in this case, I use my limb. So again, I point my hand up, and then I rotate my wrist so that I go from A to B. And I swing my hand down like this. So I'll point up, rotate my wrist so I can swing from A to B, like that, points into the board. So here, this case is out of the board, this case is into the board, which we often draw as a circle with an X in it. Imagine the tail feathers of the arrow shooting away from you. Okay. So why do we want to know all of this besides good mathematical culture? Well, the answer is because this gives us a proper definition, a vector definition of torque. So my new vector definition of torque green. Torque as a vector, which is determined by a force, is equal to R cross F. Okay, so we already know its magnitude. We've been working at it for a while. This is the definition. So that means that the magnitude of the torque vector is just equal to R times F times sine of the angle phi between them. We already know that. Okay, but then if I ask you which way does the torque vector point, the answer is it points according to the right-hand rule. Okay, so for example, if I've got a problem where I've got a wheel like this, and I apply, let's say I apply a force on the wheel, something like this. So there is my force F, and here is my radial vector R. And I want to take a cross product and see which way the torque is. So if you get confused, you're always allowed to pick those vectors up and put them tail to tail. So there is R, and there is F. That's R, that's F. And so to take the cross product, it's always R cross F, not F cross R, it's R cross F. So I go from R to F, that's pointing out of the board. By the way, I have another alternate right-hand rule for you. Some of you might like this. I find it good when I get confused and I say, well, let's double check it. It's called the right-hand rule. Well, I call it the screwdriver technique. So this only works if you're like used to using a screwdriver. So if you have a screwdriver and you've got a screw, I'm not talking about a Phillips screw. I'm talking about, this is the top of the screw that you might screw in. And if you have a normal flathead screwdriver, you take your screw and you put it in the screw and you have to turn it. And you know the rule that says if you want the screw to unwind lefty loosey, you turn it to the counterclockwise. And if you want it to screw in, you turn it clockwise. Okay. So again, screws in the US are right-handed. So what do? You take your screwdriver and you set it up so that it's coming in, so that the vector R, the first vector, is basically in the slot. And then you turn the screw so that the screw rotates from R to F. Okay. The direction that the screw goes, either out of the board or into the board, tells you the direction of the cross product. So in this case, if I'm turning counterclockwise, the screw is going to come out. That means the torque is out of the board, not into the board. Okay. Questions about that? So this is so, you know, the reason this is important is because in general, even though we've set up most of the problems in a one-dimensional way, in general, we could be contending with torques and forces in 2 or 3 dimensions. And in that case, all of these quantities would have to be dealt with as vectors instead of as simple scalar quantities. The one example that we will actually make use of that in detail is the example of a gyroscope, which we will do next week. All right. Questions about that? If I have time, I've got 5 minutes. I'll take 5 minutes to do one last thing, just so to save us a little bit of time on after the exam tomorrow. One last quantity, and I'm going to then talk about its vector nature, which actually does come into play in a useful way here. It's the last part of our analogy table. And I've got a review sheet on it that I will post a little bit later today. But I'm a little bit ahead of my lecture, so I will get started. So remember the analogies. So linear momentum. P is defined as m times v. And for now, I'll just leave these as scalars. But of course, in general, there's a vector on top of P and v, P and v. And then I can say if in a system, the system is isolated, which is say the net force on the system due to external forces, net force external is equal to 0 in that particular coordinate, then P tot equals P tot prime. And this is very useful for, in particular, for collisions. So isolated usually means not physically connected to things that would have applied forces in the direction of motion, like friction or whatever you have. So that then we carry down. So by analogy, angular momentum, all I'm going to do is I'm going to swap the linear quantities for the rotational quantities. So instead of m, I'm going to use I, and instead of v, I'm going to use omega. And I'm just going to define this as the angular momentum. And the letter physicists tend to use for angular momentum is annoyingly capital L. It's annoying because it's a lot of L's and a lot of problems, and you think we'd come up with a better letter, like A or something, but we don't. We use L, okay? That's the definition of angular momentum. In other words, you take the angular speed, you multiply it by the rotational inertia, that's the angular momentum, okay? So we got that. Now, basically, we can say if it's isolated. Now, what do we mean by isolated here? So we have 2 definitions of isolated. One definition of isolated corresponds to the net force being equal to 0 on the system. So by analogy, what does it mean to be isolated for angular momentum? By analogy, well, what's the analogy to force? What's the analog to force? Anybody? Rotational analog to force.
Torque?
Torque, yeah, right. So if the net torque is equal to 0, then we can say that the total angular momentum is equal to the total angular momentum of time. Okay? That's kind of cool. Now, it turns out this is a little bit tricky, but what we mean by it is if it's isolated is that the system is not, how can I put it? There's no twist, there's no forces that could cause a twist, right? So standing on the ground, again, that's not isolated because if somebody tries to twist me, my feet keep me from moving. So on the other hand, if I'm standing on ice, well, that's isolated. If there's 0 forces, absolutely 0 forces, well then by definition, so there's no force, there's no net force, and then there's no net torque, no external forces. But, you know, sometimes there are forces that cancel out. Sometimes there's torques that cancel out, and you can use these things. So when can you use these? You can use this in a collision. So collision of spinning bodies, right? Now, it turns out this is a little tricky because the bodies can't be spinning. If I'm going to apply angular momentum in a one-dimensional way, I have to make sure everything is lined up properly. So, for example, I could have a disk that's, so here's a disk, and it's basically got an angular momentum, which I'll call I, and an initial speed, omega naught. Okay, so it's spinning, and that disk is that's the axis of rotation. So it's kind of spinning like this in a, we'll call that a counterclockwise direction. And let's say that this is disk A, and that it basically drifts in and comes into contact with disk B. Now here I'm ignoring gravity. So like, imagine this is taking place in outer space. So here we have the same I, but we're going to say no rotation, right? And they collide. They collide, and then they stick together. So it's basically like two pancakes in space, and one pancake comes on top of the other pancake as it's spinning, and then there's syrup on top of the pancakes, so they stick together and turn together. So this is the before, and this is the after. And the after, the two pancakes are now stuck together, A and B, and they're both spinning with some final angular speed omega f. So just to make it clear, I'll color the first disk a little bit green. I'll color the second disk a little bit pink. And so when they stuck together, I've got a pink disk on top of, sorry, a pink disk stuck to a green disk. And they're both spinning together and with one speed. So this is a totally inelastic collision. And if I gave you the initial velocities, you could figure out the final velocity. That's easy, but I'm not going to give you the initial velocities. I'm just going to give you the angular velocities. So I would just want to, this is a simple application of conservation of angular momentum, So I have to check the condition. Is the system isolated? Well, these are disks in space, so there's no forces outside at all. They just collide with each other. There are internal forces due to the syrup or whatever it is that's caused the glue, that's whatever is causing them to stick together. Anything. You could have, you know, sticky, any sticky material, or you know, anything that causes them to grab onto each other. So they are isolated, so that's good. So I can say L tote equals L tote prime. So that means LA plus LB equals LA prime plus LB prime. So in this case, then that's going to be I times omega naught plus 0. That's going to be equal to, well, you know, what can I say? I can say LA has I times the final velocity omega prime plus LB. It has, since they're stuck together, they both have the same final velocity like that. So I can just solve for this, and then of course it turns out this is easy algebra. In this case, the i's basically go away, and you end up with that omega f, which you got 2 omega f's on this side, so that means you divide both sides by 2. You get omega f is equal to omega naught over 2. So that's an easy calculation here. Okay. Note that if the disks had different masses, I could actually work out what the i's are for those disks. Whatever works, you get you can get the answer. Okay. So again, as long as the system is isolated, this is my third conservation law. And you can try to apply it to a problem. So last thing I'll say today, just a conceptual framework. Got a problem sitting in front of you. Maybe things are moving, maybe things are spinning. What's your conceptual map for how to deal with the problem, right? So I'm going to erase this and just draw the conceptual map so that we have a clear idea. So again, this is mechanics. This is the material we're doing, motion. So maybe it's kinematics. Maybe if I'm asking you about positions, X, V's, and A's, or maybe it's thetas, omegas, and alphas, and I just know one of these things is a function of time, or if one of them is set to a constant, then I can just do kinematics. In other words, I'm just describing the motion. I'm not dealing with. I'm not explaining it. But if I'm explaining a motion, I have to come up with things. There's these two major branches. One is Newton's laws, and the other is conservation laws. And for Newton's laws, we have sort of two trees now. One is linear motion, corresponding to F equals ma, F net. And another is rotational, or angular, corresponding to tau net equals I alpha. And so you've got a class of compound problems in Newton, where you apply Newton's laws. So I'm asking you for forces, accelerations, all of these things. You come down this branch, you say, I'm going to apply Newton's laws first linearly, then rotationally, and then I can solve it that way. But a completely alternate way of solving the problem is conservation laws. And you've got three of them now: conservation of energy, conservation of linear momentum, and conservation of angular momentum. And each of these, the key here is that each of these has a condition. In this case, the condition is that the forces are conservative or do no work. Or in the special case of rotating bodies, the work is, the kinetic energy is taken into account by rotation. For linear momentum and angular momentum, the system is, the condition is the systems have to be isolated. But isolated here means that the net force equals 0. Isolated here means that the net torque is equal to 0. So you have to ask yourself for each problem, can I use Newton's laws? Generally speaking, you can use Newton's laws if the forces are expressed or given or implied, if the accelerations are constant or known, like in centripetal, they're known. These sort of things where you're basically given details and you're asked about forces and torques. That's where you want to go. But if you're not given these details, if you know the forces are changing and you don't have a way to contend with them, and in particular, if you have a before and an after, then you want to check the conditions for conservation of energy and linear and angular momentum. Then you can work out these things. These are them. This picture is the main picture for the course. Stuck in the middle here are these bridge concepts like the work-energy relation and the impulse-momentum relation. But almost everything else is contained in the boxes I've drawn here. And so the first part of solving any problem, especially on a third exam or a final exam, is to figure out where you are in this map. Now, for tomorrow's exam, happy news, you won't have to deal with angular momentum. That's for the final, okay? And even for tomorrow's exam, I'm not going to give you the details of rotation, at least not the extend. You don't have to do extended free body diagrams. That's just the basics. Do you know what the definition of torque is? Can you work a problem with simple rotational kinematics? That's fair game for tomorrow's exam. And so is Newton's laws, of course, at this point, and conservation of energy and linear momentum. But then these last two parts are what we'll add to the final. Okay, that's all I've got for today. Anybody have any questions about that? Basically, what I'm doing here is kind of laying out a mental strategy for tackling problems at the end of a physics course when you've got, well, it looks like upwards of 8 or 10 different concepts, and the question of how you figure out what you're going to do You have to check each idea. Is it just kinematics? Do I know position as a function of time? Is the acceleration constant? Maybe this one. Is it forces and accelerations? Well, that's Newton's laws. Do I am for energy and at linear momentum, it's off at about the final speed. So if I'm talking about speed, check these, see if you can get them. Okay, all done for today. Questions? Anybody have any questions about either today or something you want to check with me about the homework that's due later, or something you want to check with me about the exam tomorrow?
I had a question on the homework.
Okay.
For the yo-yo problem, like
Yep.
for finding linear acceleration, I know the rotational inertia is for the entire yo-yo.
Yep.
Then given the radius for just the inside axle,
Yep.
can you still do Newton's second law of rotation for that, or does it not work where they're for two different?
I'm not sure what you're asking.
The inertia is for the entire yo-yo, but the radius you're given is just for the inside.
Well, here's the thing.
Alpha.
I think you're making it harder than it is.
Oh.
Okay. So here's the yo-yo, and here's the inner radius, which I call R. Okay, you with me? So this yo-yo, I have not told you what the outer radius is. It's not known. It's not given. There's a lot of my way to tell you that it's not known and not given. But I do tell you what the total inertia of the rotational inertia of the system is. It's equal to some constant c, which is given but not specified. When I say given but not specified, I mean you could assume that c is given, but I can't tell you the number, times mr squared, where that's the mass of the yo-yo, and that's, sorry, that's little r squared. Yes?
Yeah.
Agreed? So the happy news is you don't have to calculate it, it's given. That's for the whole yo-yo. Now, it turns out that this constant c depends on this value r. It turns out a different kind, if I were to define it in terms of some other value r, this would be a different value c, but it doesn't matter. I'm just giving it to you in terms of little r.
Oh, so it's in terms of the inside radius?
It's just given to you in terms of the inside radius.
Okay.
Yeah.
I thought it was for the entire radius.
It's just the whole idea is so that you don't have to deal with big R. It's just little r. So the reason that that's helpful is because this little r, that's the I part there. And of course, when you do the torque, there's another little r, right?
Yeah.
And so some r's cancel. That makes the problem easier. That's all. That's the way I did. That's why I did it.
Okay, yeah, I was confusing myself.
Okay, great. So again, it's easier than you think. Other questions? Anybody else? Going once. Going twice. I will have office hours. I have a meeting at 5 today, unfortunately, so that means I've had to put my office hours off to 6. But if you need to talk to me about anything before then, just send me an email and I'll be happy to set up an appointment with you. All right, thanks everybody.